Okay, hello everybody, good morning. So, as we discussed in the previous report, uh, in the video, that we are going to take a look at the code for piecewise aggregate approximation and symbolic aggregate approximation. So, here we are with the Python. This time we go slightly away from the Jupyter notebook. We can get a feel and flavor of how to code using the DLE of PyCharm. So this is the PyCharm DLE in front of you. It's a virtual environment in which the Python operates. We are going to use a couple of packages over here uh, to do the approximation or modeling of the time series. Pandas we will do to transform the data frame. We will be using NumPy to transform the data frame into array so we can perform array operations. We will be using matplotlib to plot the results of the approximation, but we will not be seeing the plots here, as again it is better to see the plots in the report, because I can then better explain them over there. And the all the spade work or the hard work is done by these packages from the tslearn. Tslearn is a time series learn package which has got many methods inside, like pre-processing. It allows you to do pre-processing of the data. Then it performs the piecewise approximation, so it has got the method piecewise. And then those methods have got functionalities like performing a piecewise aggregate approximation or symbolic aggregate approximation. um, so let's get started with the code. Before we do that, also I would like to remind that as we go along, you will just see that coding a time series again or data mining again is not a straightforward one-way pipeline. Again, you would see over here that we will have to spend some effort in trying to transform and represent the data once again. So that's why we make use of pandas and numpy array. That is the way, the nature of the data mining process is, because if the piecewise aggregate approximation function needs to requires the data represented in particular fashion, we need to again transform it into a suitable representation, which can then be loaded into the method for it to do what we want it to do, right? So we are going to make use of the dataset by name mrg underscore pc.csv. We are going to make use of the principal components because that's what we discussed during our previous video, right? That we would want to make use of the independent tool to see whether the principal components, they also tell us the same story, the discovery that we made whilst performing the principal component analysis, right? So this is the place where it all gets done independently. We are choosing the RCE capital, but it will be same for all the stocks. I chose RCE capital because that was the file that I just happened to click on. There is nothing special about RCE capital stock over here. RC capital, we will be making use of component PC2, as we saw in principal component analysis, that RC capital is more closely represented, strongly represented by principal component number 2 in terms of the equivalence variance ratio, or the variance of across the samples. So that's why we choose the PC2. We then transform the subset of the data from 798 to 1196. These are the rows of the principal components uh, just for the RC. So this is the filtration operation of the rows of the principal component 2 for the RC. And the principal component 2 is in the column number 1, Python 01. So 0 would be principal component 1, In this case, 1 would be principal component 2. So we select the rows of principal components 798, 1196 from the column number index 1, which will give us the RC principal component number 2. We transform them into array, and we, with the help of the numpy method package, and once that uh, and then we pass that array to the variable RC PC2, and we keep it over there till we use it later on. We use the scalar to perform the scaling. You remember that we had last performed the scaling operation in while before doing the principal component analysis, we had done the Z normalization. We conduct the scaling operation again because, as you know, the principal component, although scaled, they still have got a range, and because all these time series are mixed up together, all the stock time series are mixed up together, the variance range could be pretty wide, right? So it is again better to scale once again just the principal component, this time just for the principal component part of it. uh, no, so it will perform the Z normalization using the TS learn package to do that, which is the time series scalar mean variance. So it tries to center the data, the PC2 component distribution data on 0, and chooses the standard distribution as 1, uh, and that is the way how you just is basically a way how you the the natural distribution you shifted to the distribution which is represented with the mean of 0 and standard deviation of 1, and then you use that the scalar to fit that transform, fit where we want to fit this data RCPC2 taking from this numpy array. Use that scalar to fit that scaling function that we do, and we pass it to something called series, which will become our new array with the scaled functions. And this is where majority of the constants for piecewise aggregate approximation get selected. We choose 50 segments. So what does 50 segment mean? We are going to choose break down the entire time series of 145,000 timestamps, or 2000, or the rows from 798 to 1196. Those windows, we are going to uh, divide them into 50 equal windows of time. That's why you choose the segment 50. You can choose whichever number suits the best. We choose 50 because it gives a better resolution of the windows. If the time series is too much, has too much fluctuation, more windows are better, because then the means representing each window would be a very close representation of that particular window. So that's how it works. But if the series is pretty steady, then you could reduce this number 50 to a less number also. Then we pass the segments to the piecewise aggregate approximation method of TS-learn, and it calculates the pieces, which basically these are the mean values for in the windows of 50. It takes the argument number of segments we want to perform the piecewise approximation, and then we do something which is fit transform on the series. So what do we want to do the piecewise approximation on? So we want to do the approximation on this series, the series which we scaled it from here. So that is what we pass as argument. It fits that approximation over here, and then we do the inverse transform of the PAA, because this approximation would just give you the mean values. We want to inverse transform. Inverse transform gives you back the data set after having performed the piecewise approximation. Uh, so that's why we do the inverse transform. Otherwise, you would just be left with the mean values, which is also fine. But inverse transform gives us back the data set represented in the form of the mean values. Uh, then we take the symbolic approximation. So PA is the prerequisite for performing symbolic approximation. Without PA, symbolic approximation cannot be done. So how does it work is symbolic aggregate approximation requires the segments which we are the PA segments. So we pass that segments from here into the SAA function, and then we give the here the another argument that you have to give, that once you have passed the PA segment, how many number of alphabet do you want that windows to be represented into. You remember we discussed the principle, the concept behind how the PA and SAX works. So I'm not going to repeat that here again, but this is where it takes those windows, and this is where it chooses the number of symbols or the A, B, C, D, E alphabets basis which you want to represent the entire time series, and then it just does the same, that it fit transform on what, on the series that we had created, the scaled series, and then we do the inverse transform, because otherwise you just get A, B, C, D, E. We really don't know what it means, but we need to get back the data represented or mapped to A, B, C, D, E. So we do the inverse transform, and that is how we get it back over here. The next part is not so exciting, that is 1D transform. Here what we do is that 1D transform, sorry, I should not be saying is not exciting, but it's a refined way of trying to model the time series. Here is the actual modeling that is what is uh, where it is get where it gets done. So you choose the number of symbols. So we have selected 10 symbol. What does it mean? That is going to choose alphabet from A, B, C, D, E, F, G, H, I, J, like that. So 10 symbols. And then it will choose the slope for its symbol, right? Because the time series would have fluctuations. It would have the functions which would be rising and which would be falling. It would have its own slope. So the slopes are given to each symbol. It represents the amount of slope carried by each symbol, because that is what is passed to 1D symbolic aggregate approximation, where it takes in the PA segments, alphabet size, slopes from here, and that is what would actually model the time series. So this is in a nutshell how you can write the code in Python for doing the approximation of the time series. I guess it's pretty interesting. Thank you.